Hello, I'm Professor Robert Beverly, and this is CS4538, Mobile Device and Wireless Security. Today we're going to be talking about weaknesses in the key scheduling algorithm of RC4, and in particular, we're going to be talking about the FMS attack against WEP. To review, WEP encryption uses RC4. RC4 is a stream cipher that generates a key stream. You can think of this key stream as being an infinite sequence of pseudo-random bytes. Of course, RC4 is keyed, and in the case of WEP, RC4 is keyed with a 128-bit key. The key is actually two parts. The first part is what we call the IV, or the initialization vector. This is 3 bytes long. This is concatenated with what we call the PSK, or the pre-shared key. Here, the pre-shared key is 13 bytes. Thus, Alice, if she wishes to send an encrypted packet using WEP, first generates the key stream by running RC4 using the key that consists of the IV and the PSK. Now, to do the encryption, because it's a stream cipher, the key stream is simply XORed with the message, byte by byte. This produces the ciphertext C. So again, Alice generates the key stream. To encrypt it, she simply XORs the key stream with the message and then sends the ciphertext to Bob. In addition to the ciphertext, Alice must send the IV. Bob receives the IV, and our assumption here is that we're using symmetric key crypto. So Bob also has the pre-shared key. Bob then is a trusted party, and Bob can reconstruct the key that was used to generate the RC4 key stream. Bob runs RC4 to generate the key stream, and to decrypt simply, again, XORs the key stream with the ciphertext. Remember why this produces the original message. Bob receives the ciphertext and XORs it with the key stream. But note that the message itself is simply the key stream XORed with the ciphertext. So here we have the key stream XORed with the message, XORed with the key stream drops out, and now we have simply the message left. We've explored WEP initialization vectors in the lab. Again, the IV is only 24 bits. And we discussed fundamental problems with the size of the IV space. For instance, we're presented with the birthday paradox and the pigeonhole principle. We're going to assume that stations adapt the most reasonable strategy, which is to use sequential initialization vectors. The point here is that each packet is encrypted using a different RC4 key. The IV changes for every packet, thus the key for RC4 changes for every packet. This is not to say that the pre-shared key changes, but instead the RC4 key changes. Let's move on from this review and start talking about weaknesses in the RC4 key scheduling algorithm. In 2001, a paper from Fleur, Montin, and Shamir was published that described ways that RC4 can leak information about the key via the key stream. At the time, this paper was dismissed as being purely academic, especially by vendors who characterized it as requiring too many packets and being completely impractical. Of course, these vendors had some commercial interests at heart. It turns out that real-world implementations of the FMS attack and implementations that improved upon this attack appeared soon thereafter. Today, variants of this attack permit full PSK recovery in WEP, and we can do it quickly, as we can induce a host to send many packets. And we'll also do this in lab. The point of this is that WEP is now considered completely broken and completely insecure, not just in ways we've discussed before, but in the sense that we can completely recover the pre-shared key. We're going to discuss the FMS attack in some detail, at least to get some intuition over what's happening here. The high-level idea is really just 3 points. Number 1, Because of the way the IV and the pre-shared key are combined, remember we concatenate the two, a passive snooping adversary has access to the first 3 bytes used to initialize RC4 in its key scheduling algorithm. Second, certain weak initialization vectors are known to set up the key scheduling algorithm in such a way that it has the potential to leak information about the remainder of the pre-shared key. And third, by gathering enough packets sent with these weak IVs, we can reliably recover the PSK. Now recall from the previous lecture that the RC4 stream cipher has 2 distinct components. The first is the key scheduling algorithm, sometimes we'll call it the key setup algorithm or the KSA, and the pseudo-random generation algorithm or the PRGA. The KSA is run before generating any output keystream, and thus it's run each time before sending a packet in WEP. The PRGA is run to generate the keystream, and it's run to generate the same number of bytes as the length of the original plaintext message. This again is because we're XORing the two. State in RC4 is maintained using a 256-byte SBox. We've seen this before as well, and there's 2 pointers, an I and a J pointer, that we maintain when running RC4. To understand the FMS attack, we want to understand some of the intermediate state of the SBox. In other words, we want to see how the SBox values evolve during each step of the KSA. So let's look at doing a partial execution of the KSA. By this we mean what we'd like to do is just run it for a couple of steps. Here, it's important to note that in the below formula, I and J are all modulo 256, while any indexes into the key are modulo the length of the key. I've kept this out just to keep the formula as simple as possible. The first part of the KSA, if you'll recall, is simply initializing the SBox to the identity permutation. The superscripts here refer to the step that the KSA has been run in. So here, let S subscript I of K be the kth value of the SBox after running the KSA for I steps. So the first thing that happens is that the SBox is initialized, that's why it's this S0, to the identity permutation. That's the first loop for I equals 0 to 255. Set each of the bytes of the SBox equal to its position in the array. Now let's look at the next part of this KSA algorithm, which also iterates for I equals 0 to 255. The first thing that happens is that J, the next J, the update of J, the new J, J of I plus 1, is equal to the previous J, J of I, plus the previous value of S sub I plus K of I. And then the next 2 equations here are simply swapping Si and Sj. So we update S of I to be the new S, or to be the old S of I j, and then we update the new S of j to be the S of I. This will all make sense more in a minute when we run an example, but stay with me for a little bit. So the first thing to observe here is that we can run the KSA for 3 steps. Why can we do that, no matter who we are, including a passive snooping adversary? Well, it turns out that, of course, the first 3 bytes of the RC4 key are exactly the IV, and the IV is sent in the clear. So let's assume that the KSA is run for these 3 steps. What happens in the L plus 1th step? So here's our formula from above. The first thing that happens here is that I is equal to L, and then we want to update J. So J of I plus 1 is equal to J of I plus S sub I of I plus K of I. But of course, I is equal to L, so we can rewrite this as J of L plus 1 equals J of L plus S sub L of I plus K of I. Of course, again, since I is equal to L, we can rewrite this as the new J is equal to J of L plus S sub L of L plus K of L. And if we rearrange terms, we get K of L is equal to J of L plus 1 minus J of L minus S sub L of L. Now, if we look at this, what we'll notice is that we have an equation with excuse me, we have an equation with 4 variables, and only 2 of these variables are known. So we can't solve this equation. In particular, J sub L and S sub L of L are known. Why are these known? Well, we've run the KSA up to step L, which means we know the old value of J, and we know what's in the S box at step L in position L. So we know these 2 variables in this equation, but observe, if we knew the new value of J, the way that J is updated, we could solve for K sub L. And if we could solve for K of L, we would obtain the next byte of the RC4 key, which would be great. This would allow us to recover the next byte after the IV. So let's take a look at what's happening in the S box. Here's an illustration with the 2 pointers. So during this partial execution of the KSA, recall that I is equal to the value of L. Remember, I is just moving along from 0 to 255. So this I pointer starts out at 0 and just moves 1 down the line as it goes through its 256 iterations. J, on the other hand, is a pointer that's moving all around. And in each step, there's a swap operation going on. So after J is updated, which means that J sub L plus 1 is set, the KSA then performs the swap of the 2 values. The 2 values being what's in the S box at position I and what's in the S box at position J. Now suppose, if you will, that this thing that J points to in the S box is some value Q. In this case, then Q is going to get swapped into the Lth position of the S box. At this point, you're probably saying, well, so what? Well, let's see. Consider that no other swaps have perturbed the J of L plus 1th element. And what I mean by that is here, the only what we're going to assume is that if you remember, the S box was initialized to the identity array. So if there's been no other swap that happened to swap that position, then at this point in time, Q is going to be equal to exactly J of L plus 1. What I mean by that is if J is pointing to, say, the 200th element, if no swaps have occurred, then the 200th element is equal to the value 200. And what this means is that the value 200, Q, will be swapped into this position I. So if there's no perturbation at that position in the S box, and if we could reveal the byte in position L, then in this case, we would have the value of J of L plus 1. This would be really cool because then we could solve the previous equation for the Lth position of the RC4 key, i.e. the next byte of the RC4 key. Now, the astute listener will be listening to this and saying, oh, these 2 conditions sound sort of unlikely. The fact that, first of all, no swaps perturb the S of I equals I initialization prior to this swap, and the ability to view inside the S box. These 2 things seem like pretty hard constraints. But in fact, as the FMS paper shows, these occur with a statistical significance higher than random. And so what you need to realize about the FMS attack is that it's really a statistical attack. And in particular, there are certain weak initialization vectors that set up this S box in such a way that these conditions are true with about a 5% probability. It also turns out that there's a large number of these weak IVs. In order to get some intuition about all of this, what I'd like to do is look at one weak initialization vector in particular. I think this example will help illustrate what's going on a little bit better. The form of these weak IVs are the 3 tuple. Remember, the IV is 3 bytes. So it's 3 bytes where L is the byte of the RC4 key we're trying to find. N is the value 256, and X is a wildcard. So here it could be any value. So let's start by running through the S box when this 3 bytes of initialization vector are observed. And in particular, what we're going to do is exactly this partial execution of the KSA. So we've observed the IV. Let's run the KSA for these 3 bytes, okay? So when we start out, we've got our identity permutation. So we've got the S box. It has 256 values. It's an array of 256 elements. And each one of these elements contains the value that is its position in the array. That's what we mean by the identity permutation. And to start with, the I pointer and the J pointers both point to the 0th element of the S box. Okay, so now let's assume that what we're trying to do is to recover the next byte in the key after the first 3 bytes of initialization vector. So starting from 0, that means that the initialization vector is bytes 0, 1, 2. And so let's assume that we've received a weak IV that has byte 3, byte 255, and then some wildcard. Okay, so that's the IV that we've passively observed. And we're the adversary trying to break this key, trying to recover the key. So we start with the identity permutation, and we've got our I and J pointer pointing at the 0th element of the S box. The first thing that happens during the KSA is that we update J. So here I equals 0, J gets updated to its old value plus the ith element of S plus the ith element of the key. In this case, the old value of J was 0, S of 0 is 0, and the excuse me, the 0th element, the first element of the key, is 3. Here, this is the first byte of the initialization vector. This means that J is now going to be updated to be equal to 3. So here's our 2 pointers at the end of updating the J pointer. Of course, the next thing that happens is that we swap the elements of the S box that I and J point to. So now the 3 is going to go where the 0 was, and the 0 is going to go where the 3 was. And there's our swap. So here's the state of the S box and our 2 pointers, I and J, after running the KSA for one step. Let's continue the process. Again, we're going to update J. So J is going to be equal to the old value of J, which is 3, plus S of I. Here I is 1. S of 1 is the value 1. Plus K of I. Here I is 1. And the byte of the key is 255. So our expression for J, updating J, is 3 plus 1 plus 255. Now, of course, this is modulo 256. So our new value for J is still 3. So J remains unupdated. Now, of course, the next part that happens in the KSA is that we swap these 2 elements that I and J point to. So now the 0 and the 1 will swap places. And that's exactly what we see in the next step of the KSA, along with the I pointer being updated to the next element. Okay, now what happens? Well, we continue the process. So J is equal to the old value of J plus S of I. Here I, excuse me, is 2. And the K of I, in this case, it points to some variable X. This whole thing gets added, and then modulo 256. This is going to equal to some value. I'm going to call it x prime. It actually doesn't matter what this value is. What's going to happen here is that our j is going to be updated to whatever this x sub prime is. I points to the value 2, and these two things will swap. And here's our new updated state, internal state on RC4. So this x prime has been swapped in. Now I points to the fourth element in the array. So I equals 3. And j is pointing somewhere off in space here, wherever x prime was. And so now we're going to do this update again. So here, j is equal to x plus s of I. Here, this is going to be the value 1 plus k of I. And here, we don't know exactly what this value is. This is what we're trying to figure out. And I'm going to say that this is equal to some value of q. All right? So here what's happened, and this is trying to be consistent with the earlier slides, is that I is pointing to this value 1, and j is pointing to some value q. And we do the swap. And this is what we're left with. We're left with this S box after running it for these 4 steps, where now we've got 3, 0, x prime, q, 4, 5, blah, 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 blah. Okay, so that's the state of our S box. Now what? Now let's take a leap of faith and let's assume that the values in the 0, 1, and 3 position of the S box remain unchanged for the rest of the KSA. This is going to be true with about a 5% probability. So this isn't always going to be true. As we move along, doing our swaps and updating our pointers, we might swap something again, right? So I moves down the line from 0 to 255, however, j is moving all around, okay? And what might happen is that we might perturb one of these positions in the 0, 1, or 3 position of the S box. But with about 5% probability, that won't happen. So let's assume that they don't get perturbed, that they remain unchanged, and that they're exactly 3, 0, x prime q, okay? If that's the case, then what is the first byte of Keystream from the pseudo-random generation algorithm? Well, let's review the pseudo-random generation algorithm. We start out again with these 2 pointers, I and j, initialized to 0. And then for as many bytes as we need output, we're going to update I equals I plus 1, of course, modulo 256. J is going to be the old value of j plus the value of the S box at position I. You're going to swap I and j and then output S of I plus S of j, all modulo 256. So let's see what happens, okay? So the first thing that happens is our I and j are equal to 0. I gets updated to 1. I equals I plus 1. Then we're going to update j. J starts out at 0, and j gets updated to j plus the ith element of S. So j is 0 plus the first element of S. In this case, the first element of S is 0 if we look at our S box up here. And so j equals 0. What is the Keystream, the first byte of Keystream that comes out of this? Well, it's S of I plus S of j, and the value of that indexed into the S box. So we know that I is 1, and we know that j is 0, so this is equal to S, the first position of S plus the second position of S, and whatever that is indexed into S. So the first element of S is 3, the second element of S is 0. If we add those two together, we get 3, and then we index into the third element of S. When we do that, that gives us exactly Q. So what we got out of here was Q in this case. Again, so what? Well, this is super cool because with this high probability, not high probability, but with higher than random probability, Q is going to be exactly this value, J of L plus 1. That allows us to solve this undetermined equation, which gives us the next byte of the pre-shared key. So this allows us to solve for the next byte because we know the old value of J, we know the old value of the S box. The only thing we couldn't solve for was the updated value of J. So that's super cool. But there's one last problem. We've assumed so far that we could observe the keystream, i.e. that we had access to this first byte of the keystream in the previous slide. But is that what a passive adversary observes who's trying to attack this system? No, the passive observer observes only the initialization vector along with the ciphertext. Well, it turns out, as usual, WEP is still quite broken in this regard. Every 802.11 frame, in fact, is wrapped in something called an LLC snap header. This is a logical link layer. The first byte of the LLC snap, in fact, is always 0xAA, meaning it's a single byte with hex AA. And in fact, the next 7 bytes are also static and well known. Therefore, in order to figure out what in fact is the keystream, we can simply take this known plaintext, which for instance is the byte AA, and XOR it with the ciphertext. That will give us the first byte of the keystream. So, in summary, how do we determine the elfth byte of the RC4 key? We've seen a bunch of slides, and this was a lot to take in. But here's the steps one by one. The first thing you do is you run the KSA through L steps. So if we know 3 bytes, we're going to run it through the first 3 steps. Then we're going to capture packets with weak IVs. In this lecture, we saw weak IVs that were of the form L, n-1, and some wildcard. We then will obtain the elfth byte of keystream, and we know how to do that. And it turns out, with probability 5%, the value in the S box at the elfth position is equal to the value of this keystream byte and is exactly equal to this J underscore L plus 1, i.e. it is that new value of J. This gives us a candidate for the elfth byte of the key. So what we're going to do is we're going to compute that candidate using this candidate new value of J minus the old value of J minus the value in the S box at the elfth position. We're then going to resolve this KL as the most frequent candidate among all of these K prime Ls. Again, it's a statistical attack, so we're going to have to observe many weak IVs and then see which are the most frequent among all of the candidates. Once we have some confidence in the elfth byte, then we move on to the next byte, and we keep doing this until the full key is recovered. So that's the FMS attack in a nutshell. I encourage you to read the paper in more detail, and you'll get some real-world experience running these kinds of attacks in the lab.